Hey guys, Mr. Betts here. Let's take a look at a few more L'Hopital rule examples that are a little bit more complicated for various reasons. The first one here, if we just try direct substitution first, we got a 0 in there, so square root of 1 is 1, minus 1 is 0, and then minus 0 over 2, that's 0. So what I'm writing down right now is what I'm thinking in my head when I'm doing a problem, and then in the denominator we also get 0. So this is going to be a problem that L'Hopital's rule is going to apply, but we want to make sure that we confirm that by verifying these limits more formally. So we plug 0 in for t here, and I already went through this mentally, but we're going to end up with 0. And the limit as t approaches 0 for the denominator is also 0. So again, this step right here is important to show that L'Hopital's rule is actually going to work, because without it, without both of those being 0 or both of them being infinity or negative infinity, L'Hopital's rule doesn't work for us. So we're going to rewrite here. We already saw the square root in the last video. Remember, the derivative of the square root function is 1 over 2 times the square root. And we do use the chain rule here, but derivative of t plus 1 is just 1. Derivative of t over 2 is going to be 1/2. So it's going to be minus 1/2 here. And all of that over 2t. So looking at what we have at this point, if we try using direct substitution again, we put 0 in for t, and we're going to get 1/2 minus 1/2 on top, which is 0, and 2t on the bottom, which is 0. We could, if we wanted to, rewrite this. And I'm actually going to do that, because if we rewrite this as a simpler fraction, I think things are going to be a little bit easier for us. So what I'm going to do is I'm going to multiply the numerator and the denominator by the common denominator on top. So really all I need to do is multiply by, 2 times the square root of t plus 1. So numerator and denominator by that. And don't forget about what we have here. I'm going to erase it to give myself a little more room. So we get limit as t approaches 0. So again, I'm just algebraically manipulating this. And we get on top 1 minus, and then the 2's are going to cancel. So all we have is the square root of t plus 1. And in the denominator, we're going to have 4t times the square root of t plus 1. Now, I did simplify the expression. However, we did introduce some complexity in the denominator, because if we're going to take a derivative here, we're going to have to use the product rule. But I do think that's going to be easier than taking a derivative here. Maybe not necessarily, but I think it is going to simplify things for us. So checking again, plugging 0 in for t, we get 1 minus 1 on top, which is 0. We get on the bottom 4 times 0 times 1, which is 0. So I want to make sure that I check those limits formally by writing them out. So this limit for the numerator is equal to 0. The limit for the denominator, and notice that I didn't need the parentheses in the denominator because we're just multiplying stuff together. That's also 0. So L'Hopital's rule is going to apply again. So we're going to take the derivative of each independently. The derivative on top is going to be, don't forget about the negative here, it's going to be negative 1 over 2 square root of t plus 1. And then the denominator, we're going to have to use the product rule here. So first function, second function. So derivative of the first is 4. Second is square root of t plus 1. Plus the first, 4t, times the derivative of square root of t plus 1. So times 1 over 2 square root of t plus 1. And I know that looks pretty complicated, but we can evaluate that just by plugging 0 in for t. And so when we plug 0 in for t, we're going to get on top negative 1/2. And then in the denominator, we're going to get 4 plus 0, because this is going to be a 0 right here. So we get negative 1/2 over 4, which is negative 1/8. This one's not obvious that it's one of those indeterminate forms that we would use for L'Hopital's rule. However, the natural log of 1 is 0. So this is 1 over 0, which is infinity or negative infinity. And 1 over x minus 1 is also 1 over 0. And so what we end up with here is infinity minus infinity. And that's not one of the indeterminate forms that I talked about, but it is an indeterminate form. So if we have infinity minus infinity, different infinities can be bigger or smaller than other infinities, so we don't know what that's going to be. So in order to use L'Hopital's rule, what I want to do is I want to write all of this as a single term by getting a common denominator. So this is going to be the same as the limit as x approaches 1. So here I'm multiplying by x minus 1 over x minus 1. Here I'm multiplying by the natural log of x times the natural log of x. So we get x minus 1 minus the natural log of x over the natural log of x times x minus 1. By writing it that way, now when we try putting 1 in, we get 1 minus the natural log of 1, which is 0, and we get 0 on top. And natural log of 1 here is 0, and x minus 1 is also going to be 0. So looking at each of those limits independently again, this numerator approaches 0. The denominator approaches 0. And so in this form, L'Hopital's rule is going to apply. So we're going to rewrite it, keep the limit part the same, take the derivative of x is 1, derivative of negative 1 is 0, derivative of natural log is 1 over x. And then in the denominator, we do have to use the product rule. So the derivative of the first is 1 over x times the second. So it's 1 over x times x minus 1 plus the first times the derivative of the second, which is just 1. So now we try doing this again, and if we think about this informally here, we have 1 minus 1, which is going to be 0. And then in the denominator, we're going to have 0 over 1 plus 0, which is still 0. So we get 0 over 0. We're going to have to do it again. So limit as x approaches 1 of 1 minus 1 over x is 0. So that's the limit for our numerator. Limit as x approaches 1 of x minus 1 over x plus natural log of x. And that's also 0. Now, before I did that, I probably should have written this complex fraction as a simple fraction. Complex fractions generally are not that easy to work with. So I'm actually going to multiply here numerator and denominator by x. And that's just going to simplify the expression for me. So again, don't forget about that work, but I need to clear some space. So this limit is going to turn into x minus 1 on top, and then x minus 1 plus x natural log of x on the bottom. Still indeterminate, so we can confirm that by checking each of the limits. Limit as x approaches 1 of x minus 1 is 0. Limit as x approaches 1 of x minus 1 plus x natural log of x is going to be 1 minus 1, which is 0, plus 1 times the natural log of 1. Natural log of 1 is 0, so that's also 0. So this that I have right here, again, we can do in our heads first, but then we do need to write it down before we use L'Hopital's rule. So limit as x approaches 1. In the numerator, we're going to get 1. That's a good sign because that's not 0, it's not infinity, so we don't have an indeterminate form at this point. In the denominator, we're going to get 1. And then product rule here, derivative of the first times the second plus the first times the derivative of the second. And just, I have an equal sign in there where I shouldn't. And then this is the x times 1 over x, that is 1. So this whole thing right here is 1. So what we end up with then when we plug 1 in for x is 1 over 1 plus 0 plus 1, or 1/2. Whew.